Hey folks, hey, thanks for joining me here today. I'm sure you're well aware, and we've heard it for years really, that the worldwide data footprint is growing. I think about it a few years back. I remember thinking about that thumb drive, that coveted giveaway at conferences and such. And folks started talking about zettabytes of data, literally billions of those thumb drives worth of data being generated every year. And I couldn't really wrap my head around it. How could we store all of that data, and how expensive would it be to do so? And perhaps most importantly, what are we going to do with it all anyway? How can we access it? How can we search it and derive insights from it all? Well, first of all, my eyes grew wide when I saw the sheer size of IDC's predicted Datasphere, what they call the global amount of data that's created and replicated every year. Well, last year we came in at just over 64 zettabytes with a 23% compound annual growth rate for the next 5 years. But it came as some comfort to find out that a lot of that data is ephemeral. In other words, it's used by an application and then it's discarded. So only 6.7 zettabytes is actually stored for what IDC calls the global storage sphere. Yeah, okay. Did I say only? That's really massive. And although it's not quite growing at the same rate as the data sphere, it's pretty darn close at 19% CAGR. Now, really to put this in perspective, imagine all the data we've amassed since computers have been around. Over the next 5 years, we'll more than double that. IDC Research Vice President John Riding recommends that organizations should prepare to store more data along with their digital transformation initiatives so they can accelerate their data analytics, driving business insights. Now, I'll contend that one of the best ways to do that is by embracing object storage. But first, it might be prudent for me to talk a little bit about the different storage protocols, and that's file, block, and object, and where each one fits. I'm not really advocating that everything move to object, but embracing object storage will help manage this onslaught of data and make it useful for data analytics, business intelligence, and emerging workloads like artificial intelligence and machine learning that we've all been hearing a lot about lately, right? So first, there's file storage. And I think most people are familiar with this. If you think about your first interactions with a PC, for example, that used a file system protocol, it's hierarchical, similar to a file cabinet. I remember back in the 90s, I had a manager with a couple of file cabinets in his cube, and one of the drawers was labeled maps, and then within that drawer there were folders in the drawer, A through D, E through H, so on and so on. And then in the folders there were actual road maps for states and cities, and he grabbed one of those as he rushed out to the airport. I mean, man, I was really glad when MapQuest came about. But anyway, I digress. That's the same hierarchical idea behind a file system. Files are stored in folders within a directory, and then they're accessed via different file system protocols, typically SMB if you're running on a Windows machine, or NFS, Network File System, for Unix or Linux environments. And they're typically written and subsequently accessed as a whole on a disk partition. Now, typically, if you want to share a file and collaborate with somebody, you can share your drive via the network or through a network area storage or NAS device. These were deployed to let many people share a repository of files within a team. Well, now the nice thing about file storage is that it typically has high throughput at a reasonable cost, and you can tier different data across different types of media for better performance. So, you could have cold data sitting on spinning devices, you could have hot data sitting on flash or NVMe devices. It's also inherently POSIX compliant, and many applications are already written expecting file protocol for access, so it's pretty ubiquitous. Now, from these standpoints, file is a simple choice, but it can be difficult to scale, not only capacity, but accessibility. Think about it this way. When you want to access the file, your machine has to go and find and load that file into memory, and it has to do so for the complete file. Now, that's typically not a problem if you're working on your computer, but imagine if the file is very large and suddenly a lot of people are trying to get to it at the same time. it can bring up network issues. It can bring up bottlenecks in your network. Now, there are some software-defined storage solutions that have workarounds, like lazy I/O, for example, in Red Hat Ceph Storage to help with this issue. But still, file systems don't scale very well, and it becomes difficult to manage as it gets larger. Also, the metadata. That's the data about the data, like when the file was created, where it lives in the directory, the size, all of that type of information. That metadata is very limited in a file system. This makes it a lot harder to search. And, sure, you could put more information into the file name, but then that becomes long and cumbersome. So, how do you divide up and adaptively balance that metadata? This ushers in most of the complexity, both in system implementation and in workarounds. Now, suffice it to say, file storage does have its place. It's great if you have smaller teams who need to collaborate and share a number of files. But, I'm sorry to say, it's not going to get us to solve our data growth issues that we mentioned before. So let's consider the next thing. Let's consider block storage. This is a much more efficient way to store and retrieve data. Essentially, your application takes all of your data and cuts it up into chunks of uniform size, typically 4K or 8K blocks, and then distributes those chunks across volumes. Now, another great attribute is that your application can include resiliency features in the way that it writes the chunks across volumes. Now, while in file storage you had limited fixed metadata, actually with block storage you don't really have metadata at all. Instead, everything is mapped by file location and it's stored in an index somewhere on file, on a database, etc. And when it comes time to retrieve that data, the application looks for the map of where the chunks are located and then pulls them back together so you can see that file. Now, typically, block storage is stored on a storage area network or array. That's normally what we see out in data centers, and those are directly connected to the servers running the application via a fiber channel or an iSCSI interface. And there's typically 2 or more controllers in an array that handle the writes and reads across volumes that are created across actual physical media, physical disk. Now, the great thing with block storage is that it's very fast with high inputs and outputs per second, or IOPS, and low latency, meaning that your application response times will be much faster. Now, block systems can also be accelerated by implementing all-flash devices, which, of course, are much more expensive than spinning disk. But since a lot of the data stored in block devices are prone to inefficiencies, making use of compression and deduplication topologies can sometimes greatly reduce the usable disk space, and thus you optimize your raw capacity. Now, all that said, block storage is very expensive in general, and it doesn't scale much more than a petabyte within an array or a SAN, etc. Likewise, the data is typically held close to the application, and that implies complexity as you plan for your business continuity scenarios. And still, it's great for structured data. Typically if you're looking at databases, especially transactional applications that store a lot of data in a relational database, think of your human resource management type applications, financial applications, AR, AP, stuff like that. It's also good for virtual machine environments. All right, so now we're going to talk a little bit more about object storage. Now, this is very different because it stores everything in a flat namespace. The data is chunked up, somewhat similar to blocks, but instead of being distributed across volumes, it's written in objects to the same object bucket. Now, the objects are made up of the data itself, along with metadata and a unique identification key. Now, the great thing is that this metadata is highly customizable, not like file storage where you can only have a set of static type metadata, or you could rewrite your application to customize it. With object, the metadata is inherently very customizable with tags, so that when someone wants to search for the object, they can do so either by knowing the key or by searching on something that might be stored in the metadata. Typical protocols for object storage are Swift for OpenStack private cloud environments, or especially the S3 protocol originated by AWS, which has pretty much become a de facto standard for cloud object storage. Now, depending on the architecture of the object storage software, you can typically accelerate performance by attributing a small amount of the expensive all-flash devices, NVMe devices, etc., for the metadata cache, while optimizing costs with hard drives supporting the overall data layer. This also allows you to increase usable capacity, having an option for erasure coding data resiliency versus pure replication, depending on your workload. Now, finally, object stores are typically built on a distributed scale-out architecture that continues to add capacity at near linear performance virtually indefinitely. This means really that object storage is massively scalable. It easily handles tens or even hundreds of petabytes per cluster. Enhanced access controls and policy features provide secure access for multi-tenants, and it can handle access by many devices all at the same time, as well as massive parallel ingest, which makes it perfect for cloud storage. Now, I mentioned a distributed scale-out deployment, but this also means that you can perform rolling hardware upgrades while your data is live. Now, object storage is also characterized by high throughput, and importantly, as we're dealing with massive data growth, object storage really has the lowest cost per gigabyte available. Now, object storage does tend to have a slightly higher latency, but you can tune your environment and follow some architectural best practices to mitigate some of that. And a lot of the traditional applications weren't written for object, but as you're planning your digital transformation, you should focus on modern cloud native applications that take advantage of object stores. And older applications can be revamped or replaced over time. So overall, as you can see here, object storage is great for large amounts of unstructured data and cloud native applications. It also makes a great place to store media, backup targets, archives, as well as creating a data lake for large-scale analytics and some of these new things around artificial intelligence and machine learning modeling type workloads. Okay, so why is all of this important? Well, according to a survey by 451 Research, more than half of respondents said that most or all of their application development is now cloud native. Okay, so maybe you're wondering, why are you hearing about data and storage methodologies from Red Hat? After all, we don't sell disks or servers, but we do, however, provide a portfolio of data services solutions that simplify access to data when and where you need it, and we deliver a consistent user experience regardless of how you're accessing that data. And our solutions provide massive scalability with deterministic performance. And we build these data services upon a software-defined storage foundation called Ceph. All right, so what's Ceph? Well, of course it's open source. Everything at Red Hat begins with open source. And in the community, the Ceph project began about 19 years ago. And in that time, there have been 16 releases. So the current community release, Pacific, is the upstream of our Red Hat Ceph Storage 5 release, which will be coming out very soon. And as you might guess, yes, Ceph is massively scalable. We have customers running hundreds of petabytes in a cluster. And it's based on a flexible scale-out architecture. So not only is it great for the aforementioned scalability issue, but think of it this way: if you're deploying an array with two controllers, for example, and one of the controllers goes down, your performance will degrade enormously. And you'll probably have to schedule some downtime to replace the failed components. By contrast, Ceph is built on industry standard servers and storage, so if you lose a single server in the cluster, you're only losing part of your performance. And it's self-healing, so you just bring in another server into the cluster and the cluster rebuilds while it's live. You can even expand your cluster or perform hardware upgrades while your data is live. And best of all, Ceph is very flexible. It runs file, block, and object protocols natively, so you get the best of all worlds. It's API driven, so it's very malleable to support a plethora of workloads, and it's proven for emerging technologies such as cloud native applications and AI ML workloads. And yes, indeed, I did say that Ceph can handle all three storage protocols that we talked about today: file, block, and object. But how does it do that? Well, one of the main components of Ceph is RADOS, because a three-letter acronym is never enough, right? RADOS stands for Reliable Autonomic Distributed Object Store, and this is the backbone that writes to the object storage daemons, or OSDs, that are mapped to physical storage. But above all of this are gateways that manage data through an API library called Librados. And these gateways allow applications to interact with data across the file, block, and object storage topologies. If you're interested, a colleague of mine digs deeper in this video that I've linked here. So once you get the slides, download the slides, you'll be able to follow that link. Okay, so if Ceph can handle all three storage topologies, then obviously there's a lot that you can do with it. So, one use case we've had a lot of interest in is in building an architecture that allows you to scale compute and storage separately for large-scale analytics. Typically, organizations who deploy Hadoop clusters run into scalability issues. Actually, Hadoop scales very, very well, but you cannot disaggregate your compute from your data. So typically, as you add more and more teams to or users to that environment, you end up with excess bandwidth in some part of your architecture. So lots of folks, the way that they overcome this is they create separate clusters for different teams or business units, etc. And one customer we worked with actually had over 50 clusters running. Now, not only does this become very expensive because you have duplicate data sets, but then you have to replicate parts of your data across multiple clusters. That can be error prone. It's a lot of work, and users are never sure if they have the latest copy of their data. So to solve this problem, we worked with a number of organizations across the globe to implement an architecture where they could support multi-tenant application access for their users while having a common shared data context built on Ceph. And a lot of companies also deliver object storage as a service to users at large, or even consortiums where you want to share data with many entities, many research facilities, or universities, for example. One nice benefit is that you can deploy a multi-site active-active cluster with single namespace across multiple geographic locations, and the clusters synchronize, allowing users to read from or write to the closest one in that cluster. And I mentioned a little bit about OpenStack briefly before, but if you're not familiar with it, OpenStack is a platform for delivering private cloud services for organizations. Typically, we find OpenStack being used to virtualize network functions for telcos and to manage private clouds in banking or financial services, but there are many other industries using it as well. For the storage backbone, over 60% of OpenStack deployments use Ceph. It's probably due to its scalability and flexibility to serve file, block, and object protocols through the various OpenStack APIs that you see here. And Ceph also provides a great object data store for backups and archives. So you can see here a number of industry-leading data protection solutions that have been validated with Ceph Storage. We've been working with a number of these folks and a number of others to support a backup of OpenShift environments as well, which is slightly different because your persistence is kept at that storage layer, and you have to be able to back up and restore based on context of that cluster. So Ceph ends up being a great backup target for those types of workloads. Here's a workflow. It's particularly near and dear to my heart. As I mentioned before, objects are written and stored in an object bucket. Now, with Ceph, you have the ability to create object bucket notifications that are sent to endpoints such as HTTP or Kafka when an object enters the bucket, or if it's modified, or even when it's deleted. And with these notifications, you can spawn off events that automate a data pipeline in real time. This particular example shows what happens when an X-ray image comes in from an edge device in a clinical setting. Now, once the image lands in the bucket, it creates a notification to a Kafka stream that invokes an AI inference model to assess the risk of pneumonia. If the risk is low, in this case less than 30%, it sends the image to the patient record. Now, if the risk is somewhere between 30 and 80%, it stamps the image for follow-up by the medical staff. But if that risk is over 80%, it immediately notifies the doctor, and a separate application stream anonymizes the patient personal information, so you're in compliance with legal issues, and then it sends that image back to the data science team to help retrain the model. Now, OpenShift Serverless, or Knative, is actually the piece that spawns these applications automatically depending on how many images are written to the bucket. So, if you don't have to worry about expanding the cluster when loads are high, nor do you have to have idle capacity when loads are low. Now, this is just one example of what you can do by automating a work stream. We have a lot of other demos, like a smart city example, an automated payments example, and you might even automate insurance claims or use fraud detection to manage credit approvals. It's really a really elegant example of automating transactions that used to be processed in batch. Now, we also have another offering called Red Hat OpenShift Data Foundation. Now, this provides the data service layer for OpenShift clusters to simplify day one and day two operations, as well as putting resources in the hands of the users, whether that be an application developer, data scientist, analyst, or, as we just saw in the last example, even in the hands of an automated process. OpenShift Data Foundation is built on Ceph, providing the persistent storage services for the cluster, and of course, once again, file, block, and object storage classes. And OpenShift Data Foundation also integrates Rook that manages the storage orchestration within the cluster, and a solution called Nuba that provides a multi-cloud object gateway for data federation and management across hybrid and multiple public cloud platforms. But in my mind, one of the most important things we do at Red Hat is to prove that the solutions work, and not with some contrived benchmark that just makes us look good, but we're actually trying to break things so that we get a good idea of what works well, how to tune for different environments, and what doesn't work well with other people's products. No, well, that's a little tongue-in-cheek, but in reality, there's a lot that we learn from running various tests, and it's something that we don't just do to make our solutions better, but we do all of this work to help the community at large with these types of solutions. Okay, so we started off this presentation talking about how object storage is not only massively scalable, but how it's grown in recent years to be applicable for high-performance computing. Well, let me just say that object storage itself has evolved. There have been a number of performance improvements in the software itself, as well as constantly adding new features and functionality. But the evolution of the industry has, in no small measure, made a huge impact on the role of object storage. So faster networks not only enable better throughput through the Ceph cluster itself, but it also provides us with those fast interlinks between data and applications. And GPUs accelerate parallel processing for a lot of HPC type workloads, and the combination of larger capacity, better endurance, and lower cost of NVMe drives today has opened up a lot more possibilities, not just for all-flash clusters, but also for multimedia clusters that provide best-in-class performance for different workloads. Now, as well, the accelerated adoption of containers for mission-critical production workloads and the integration of application services and data services really completes out that whole modernized platform. Now, just one of the several performance improvements that have come over the past couple of years comes at the hands of a new object backend called BlueStore. It was actually introduced in upstream code a few years ago, but we spent some time to stabilize it and harden it before we were able to introduce it into production for general availability with Red Hat Ceph Storage, which was about a year and a half ago. Today is our default backend, and we have shown incredible write performance increases in tests that we've run, as well as a number of our partners have done some testing with BlueStore versus the old backend called FileStore, and shown massive improvements in the write performance for those types of workloads. And just last year, we worked with an analyst firm called Evaluator Group, along with Intel and Seagate, to push the limits of our system by running a 10 billion object performance test. Now, only a year prior, we had published results for 1 billion objects, but we wanted to see if performance was sustainable. And the results were great. Not only were we able to show deterministic performance throughout the test, but as you can see here on the right-hand side of this graph, we saw when the performance started to wane. And we were able to determine that the Intel Optane drives that we were using to accelerate our metadata cache were becoming saturated at this point. So, add more NVMe capacity and we could have sustained this performance even further. It's really great to do tests like this because we can show people what they should expect, even in an unlikely scenario such as running 10 billion objects. I've linked some additional material here, so when you do download the slides, you can get to these links and read more about this. Now, we were also working with Penguin Computing and Seagate on a customer POC for an AI ML workload that got excellent sustained throughput, which prompted Penguin to offer a solution based on our findings. We're in the process of publishing blog series highlighting the tests, but you can also find additional information in the Penguin solution guide that's linked here. Now, likewise, Micron has done a lot of testing with Ceph, and they've published numerous reference architectures showing performance for both object and block storage workloads on various all-flash architectures. The linked blog post here discusses some of the results and provides links to the current reference architectures that are out there. But I'm also very happy to note that Micron will soon be releasing their next generation of drives, and we look forward to seeing additional results with Ceph and OpenShift Data Foundation in the very near future. Now, Intel has also been a great partner, not only working with us on some of the aforementioned projects, but more recently on tests for various workloads such as PostgreSQL databases, Starburst Trino, what used to be known as Presto SQL, and more recently IBM Analytics Engine, which is their distribution of Apache Spark. Now, these tests and others have been conducted in Intel labs that have led us to recommending numerous configurations for edge, capacity, and performance workloads. Now, likewise, Dell has pulled these configurations into their ready architectures for OpenShift. You can find more information by following some of these links in the slide deck. Dell Technologies datasheet will have prescribed bills of material to go out and order these solutions and make those available right away for your OpenShift clusters if you would like to do that. You can also find some additional information about Red Hat Data Services and Red Hat Ceph Storage on the web. And I'd also invite you to download this great ebook that I have listed here that discusses some of the industry evolution on intelligent applications and data pipelines. Now, this is more based on industry evolution rather than on any products per se, but I think it's a great read. It's under 100 pages, so it shouldn't take you too long to get through it, but it's a very enlightening ebook if you'd like to take a look at that. And also, if you'd like to schedule a demo or a workshop or executive briefing, best way to do that is to talk to your sales rep. But if you want, you can fill out the form that's linked here, and we'll put you in touch with somebody right away, and we'll get that going as well. Now, finally, before I leave you today, I've talked a little bit about some of the technical proof points that we've done, benchmarking, etc. But I've included a number of additional workload proof points. Things from Crunchy Data Postgres to IBM DB2 Data Warehouse, Starburst Trino, Jenkins, a few others. But I've put them in the backup slides so you can take a look at those at your leisure if you have any particular interest in a particular workload. And, of course, check us out and follow our social media channels or send us a note if there's anything that we can help with. With that, I'll bid you adieu. Thank you so much for joining me today and enjoy the rest of the conference.